What if I told you that right now, China is developing a train capable of reaching speeds of up to 1,000 km/h, 621 miles per hour. That's so fast it could take you from New York to Los Angeles in just over 2 hours. To put that in perspective, Japan's famous bullet train, the Shinkansen, typically runs at around 320 km/h, or 200 miles per hour. The fastest commercial Maglev train currently in service, the Shanghai Maglev, tops out at 431 km/h, or 268 miles per hour. Now imagine a train that more than doubles that speed, traveling even faster than many commercial airplanes, which cruise at about 925 km/h, or 575 miles per hour. Think about it. A trip from New York to Chicago could take just 90 minutes. Right now, that same journey takes around 12 hours by train, or 2 hours by plane, not including all the airport hassle. In today's world, we're always searching for ways to make travel faster, more efficient and more connected. We've moved from horse-drawn carriages to cars, from propeller planes to jet aircraft, and now we're standing at the edge of a breakthrough that could make even our fastest trains seem slow. This is the story of the T-Flight, Maglev vacuum train, a technological marvel that has the potential to completely redefine high-speed travel. But before we dive into what makes this new system so revolutionary, let's take a quick look at how we got here. Back in the early days of trains, steam engines were considered cutting edge. Hitting 48 km/h, 30 miles per hour, was seen as incredibly fast, especially compared to horse-drawn carriages. Cars followed soon after, typically running at 64 to 80 km/h, or 40 to 50 mph, which at the time seemed lightning quick. Then in 1964, Japan introduced the world's first bullet train, the Shinkansen, which could reach 210 km/h, or 130 miles per hour. This was a game changer, cutting travel times dramatically and reshaping how people moved across the country. Over the years, these trains improved further, with some models now running at 320 km/h, or 200 miles per hour. China pushed the limits even more. In 2004, the country unveiled its first commercial Maglev train in Shanghai, hitting 460 km/h during testing and running at 431 km/h in daily service. At the time, this was groundbreaking technology. The train connected Pudong International Airport to the city center in just 8 minutes, covering 30.5 km of track. But for China, that was only the beginning. The Shanghai Maglev, while impressive, was built using German technology, and China wasn't content to stop there. And if there's one thing we've learned about China over the past few decades, it's that they don't like relying on foreign technology for long. By 2016, China had already developed its own Maglev system in Changsha. Now, this train was slower, running at about 100 to 120 km/h, but it represented something far more significant: China's ability to design and build Maglev systems independently. The Changsha line cost about $750 million to build, and while that might sound steep, it's actually relatively modest compared to many other major transportation projects. Each train carries 363 passengers, and the line has been operating successfully for years. Every one of these developments marked a major step forward for its time. They didn't just push speed, they reshaped how we think about travel, commuting, and even city planning. Cities that once felt far apart suddenly became connected, and long-distance commuting became a realistic option. When you see this progression, it's easier to understand the new breakthrough on the horizon. Transportation keeps evolving. Each leap builds on the last and expands what's possible. Fast forward to today. China's Aerospace Science and Industry Corporation has stepped in, and they aren't just aiming for slightly faster trains. Their goal is to revolutionize ground transportation altogether. The new system they're developing targets speeds of 1,000 km/h, nearly the speed of sound. How do they plan to achieve it? By combining two advanced technologies: magnetic levitation and vacuum tubes. Now you might be thinking, wait, isn't this basically Elon Musk's Hyperloop? Well, yes and no. Both concepts aim for super high speeds by reducing air pressure in tubes. But the designs and methods are different, and we'll get into those details in just a moment. For now, think about it this way: what's the single biggest force slowing down any fast vehicle? air resistance. As speed increases, the air in front of you becomes like an invisible wall. That's why today's fastest trains top out around 500 km/h. Beyond that, they're simply battling too much drag. This new system solves that problem by running the train inside a low vacuum environment, which dramatically reduces air resistance. That's what allows for those record-breaking speeds. So what exactly is Maglev technology? Well, Maglev stands for magnetic levitation, a method of transportation that uses powerful magnets to lift and propel trains instead of rolling on wheels. These trains essentially float on a magnetic field, eliminating friction with the track. The idea of magnetic levitation isn't new. It's been around since the early 20th century, when pioneers like Robert Goddard and Émile Bachelet first proposed using magnetic fields for transportation. But only in recent decades have we seen the concept brought to life on a large scale. Now let's break down how it works. Traditional maglev trains hover about 10 millimeters above the track. But this new system, it levitates at 100 millimeters. That's 10 times higher. This extra clearance reduces interference and makes operation far more stable, especially at ultra-high speeds. To hit those speeds efficiently, the trains are being built with carbon fiber materials, lightweight but extremely strong. It's not just about going fast, it's about going fast efficiently. A big part of that efficiency comes from superconductivity. The system they're using is based on superconducting maglev technology. Here's the clever part. When certain materials are cooled to very low temperatures, they become superconductors, meaning they can conduct electricity with zero resistance. This makes the magnetic levitation more powerful, more stable, and far more energy efficient. And you might be wondering, okay, but does this actually work in practice? So far the answer looks like yes. In Shanghai province, they've already built a 2-kilometer test track. Now 2 kilometer might not sound like much, but it's plenty to validate critical systems at high speed. And the results? They've lined up closely with what engineers predicted on paper. That's huge, because it's one thing to do the math and say something should work, and it's another thing entirely to see it actually perform in the real world. During these tests, engineers focused on several key aspects. Precise navigation. At 1,000 km/h, even the smallest deviation could be catastrophic. The system has to keep the train locked perfectly to its intended path. Stable suspension. The train must maintain a consistent height above the track, with no wobbling or fluctuations. This isn't just about safety. It's about ensuring passengers feel comfortable at speeds where stability is everything. And finally, let's talk about safety. Because being able to go fast is impressive, but being able to stop safely is just as important. The tests showed that the system could bring the train to a controlled stop from high speeds, proving that the fundamental concept isn't just theory, it works. The next challenge is scaling it up to longer distances. So what does this mean in practical terms? If trains like this become reality, they could create what economists call one-hour economic circles. That means entire urban regions where any 2 points are less than an hour apart. Think about what that could change. You could live in one city and work in another hundreds of kilometers away without needing to move. Long-distance relationships? Suddenly much easier. Cities that used to feel hours apart could feel as close as different neighborhoods within the same metro area. And there's another huge benefit, the environmental impact. If these trains start replacing short-haul flights, we could see a dramatic cut in carbon emissions. Aviation is one of the biggest contributors to greenhouse gases. To put it into perspective, typical short-haul flight emits about 150 to 200 grams of CO2 per passenger per kilometer. Conventional high-speed rail comes in at just 20 to 30 grams. A maglev vacuum train could cut emissions even further, offering one of the cleanest ways to travel at scale. But let's pump the brakes for a second. As exciting as this sounds, there are major challenges ahead. The biggest one, cost of building low vacuum tubes over long distances, is incredibly expensive. And integrating such a system into existing rail networks adds even more complexity. For comparison, conventional high-speed rail can cost anywhere from $17 million to $170 million per kilometer. Depending on terrain and design, a maglev vacuum system could easily surpass that, running into hundreds of billions of dollars for a single long-distance line. And then there's safety. At speeds approaching 1,000 km/h, even the smallest technical failure could have serious consequences. The engineering, redundancy, and safety protocols for such a system would have to be absolutely flawless. Of course, when you're traveling at nearly the speed of sound, the emergency systems need to be absolutely foolproof. Safety has to come first, and it's worth noting, China isn't the only country working on this. Japan has been developing its own superconducting maglev, the Shinkansen, designed to run at speeds up to 505 km/h, 313 mph. While not as fast as China's proposed system, it's still groundbreaking, and it's actually under construction. The first phase aims to connect Tokyo and Nagoya by 2027, with plans to extend to Osaka in the following years. Meanwhile, in the United States, several companies are pursuing versions of Elon Musk's Hyperloop. Like China's T-Flight, it uses low-pressure tubes, but instead of levitating trains, Hyperloop uses passenger pods. The target speeds are even higher, around 1,200 km/h, 760 mph. But here's the difference. Hyperloop is still mostly on the drawing board. Even Virgin Hyperloop, once the frontrunner, has shifted away from passenger transport. China, on the other hand, is building on decades of Maglev experience. They're taking an evolutionary approach, starting with conventional Maglev, then scaling up step by step instead of jumping straight into untested concepts. That steady progression might be what gives them the edge. So what do you think? Are you ready for a world where you can zip between cities at the speed of sound? Or does the thought of traveling that fast make you a little uneasy? Let me know in the comments below. I'd love to hear your thoughts. As for me, I can't wait. The idea of having breakfast in Beijing, lunch in Shanghai, and dinner back in Beijing all in the same day is absolutely mind-blowing. Who knows? Maybe in a few decades, this kind of travel will be as common as taking the bus is today.